So, I want to mention this thing. I mentioned it briefly in the past, a little bit, called the collision theory. And it basically talks about what has to happen in order for a reaction to occur. Well, basically then, if you imagine, let's say, a beaker or a room full of air trying to react, whatever it is, first thing is, those molecules have to actually collide, right? They have to actually come into contact to react. They can't just react if they're across the room from each other. So, the first one is, when they collide, they have to have enough energy to actually begin breaking apart the bonds in the reactants to free them up to recombine in the products. That's the first thing. You've got to have enough energy for them to break. The next thing is, though, when they collide, they have to collide the right way. You can't just stick them together however you want. So I always think of it kind of like Legos, for example. If you want to combine Legos, well, you have to click them together in the right orientation, right? So they'll actually connect and stick. So same thing with molecules. So for example, let's look here at N2 and O2 trying to make NO. Well, if I'm going to make NO, I have to have a few things. The N2 and the O2 have to collide. They have to collide hard enough to actually break apart the nitrogens and oxygens and then recombine them, like you see here, to make NOs. Well, the orientation is important because if they collided, let's say, end to end, well, that wouldn't work because you wouldn't get out an N and an O and an N and an O connecting. So it's also how hard they hit and the orientation with which they hit. Okay, and then that third part is now we've broken them apart, and now we have to recombine them back together in the products. So that's three different pieces that have to happen in what's called the collision theory. So our goal then is to try to use this theory and figure out, okay, well, how can I try to increase the likelihood that our collisions will have enough energy and they'll collide with the right orientation. And if we can master those pieces, then we can make our reactions faster and more sustainable, which is what we want. So, again, if they collide and they don't have enough energy, well, they just bounce off each other. It's kind of like Legos. If you use the right Legos, you kind of have Legos. You try to put them together. Well, we kind of, gently tap them. They won't stick together. So you got to have enough energy to actually connect. And then, like I said, if they don't have the right alignment, then they'll just, like I said, they're not the right way or twist it around. Nothing's going to happen either. So our goal is to give them enough energy and to give them a chance into having that right alignment or orientation. Okay, so when a reaction occurs, we can write what's called a little reaction diagram like this, where we have the reactants are on the left side, so reactants going to products. And there's always this little barrier that you have to get over between the reactants and the products. And that barrier is called the activation energy. So that is basically, it's the minimum amount of energy you need for the reaction to take place. Or another way to think about it is that minimum amount of energy you need to break apart the reactants and get them ready to recombine. So it's like a little hill you got to cross. So every reaction has some kind of an activation energy. Now the reactants could be, of course, various places. There's always going to be some kind of a little hump or a little hill in between them. That little hill you have to get over to get to your products is the activation energy. Okay, so one second. So we abbreviate that. I'll see you over here. Let's see, by the way, everybody says E, capital E with an A, the activation energy. Okay, well, our goal, like I said, is figure out, well, how can I make my reactions actually fast enough they will actually be useful to me? So that the speed of that reaction, trying to get them over that hump as quick as we can, that's called the rate of the reaction. And the rate is just like the rate of your car or the rate of something, traveling. It's how fast are you changing in a certain amount of time. So in our sense, it's not change in miles per time, like hour, it's change in concentration per time. So how much of that reactant is being used per time. Or you can measure how much of that product am I making in a certain amount of time, per second, per minute, per day. So just change in concentration per time. Again, you can do it either way. Either reactants are being used up, you can measure that, or you can measure how much products am I producing. It'll be the same kind of thing. Okay? So, how are some ways I can try to affect that? One is the temperature. So, if I increase the temperature, let's say, of a reaction, what does that do?
Increases the reactions.
More collisions. Yes, because it makes them move faster, right? So yeah, the hotter they begin to move faster, means they're going to have more collisions. So you have the greater likelihood of them colliding with the right orientation they need. What else is going to happen though with them as they are colliding if they have more temperature?
Pressure.
Well, the molecules are moving faster and faster, so when they collide, what's going to happen with that collision?
React faster.
I mean, why? The reaction's based off a couple of things. They got to have enough energy to actually break the bonds, and they got to have the right orientation. Well, temperature helps both of those because they're colliding faster. They're going to have more energy when they collide, right? So they're going to hit harder, which is more likely they'd have enough energy to snap those bonds apart in the reactants. So yes, it does that. It does give them more energy. And like I said, if they're just bouncing around faster, they have a greater likelihood of them colliding with the right orientation. They're banging each other 1,000 times a second instead of 100 times a second. So it helps both of those. It helps give them the energy and the likelihood for the orientation. Another thing we can do is just add more of them. So just dump in more of your reactants. So it was 1 molar, we'll make it 6 molar, or make it 10 molar. Well, again, if you have more molecules, now you've got more collisions, right? So you're going to have a greater likelihood of you having the proper collisions with the right energy and the right orientation. So changing the concentration just gives you more collisions, right, going on. And the third thing we have to discuss is this thing called a catalyst. A catalyst. And a catalyst really helps to solve that problem with the orientation. Now our body has a bunch of these catalysts, and they're called enzymes. And enzymes' job is to basically to try to take reactions that would normally be way too slow on their own, and to catalyze them and make them much faster. Okay, so temperature makes them move faster, gives them more energy, right? So that gives them more energy in their collisions and a greater chance for the right orientation. Concentration, again, so just more of them banging into each other, so more collisions. And then this one, like I said, will solve the orientation problem. We'll see that here in a second when we look at the enzyme. Okay, so I was going to briefly mention these. I kind of told you all that I was going to quickly go through this. Temperature, more kinetic energy, so they move faster. They get more collisions. And then they have a greater likelihood of them colliding with the right way. For example, this is why you put things in the refrigerator. Because you want to slow the collisions. You don't want things to rot and spoil as quickly as they would just sitting out there. So same thing, right? So hotter, more collisions, faster reactions. Colder, less collisions, slower reactions. So that's that one. Now how about this one then? Add more of them, like we said. More collisions that way, right? So you add in twice as many or 10 times as many. Just getting more collisions, so your greater likelihood of having the right kind of collision, the right orientation. That's going to increase the rate. And the last one, the catalyst. Now, the catalyst, what it does is it basically takes that little hump you have to get over, called the activation energy, and it lowers it. It makes the hump not as big. So if this was the activation energy before the catalyst, maybe this is the activation energy after the catalyst, the lower hill. So it just makes it easier for you to get from products to reactants. Now, it won't change the reactants, it won't change the products, it just makes you get faster, get there faster between the two. Okay, so, one of the things I mentioned is about a catalyst. One of the unique things about catalysts is they are not really a reactant, they're not actually being used up. So it's there the whole time. So all it does is it turns reactants into product, turns reactants into products, but it's not being used up. Okay, so it's not a reactant that you're using. It's used over and over and over and over. So yeah, that's a biggie. So for example, like I said, enzymes are your body's version of that. So an enzyme, for example, is not used up every time it catalyzes a reaction. It can catalyze millions of reactions every second or every minute, but it's not being used up. It just pulls in what it needs, spits out the products, pulls it in, spits it out, pulls it in, spits it out. So for example, as I said there are dozens, hundreds of reactions in your body, that would not actually occur at just normal body temperature. So you don't have the viable option of just trying to heat up your body and make them go faster, right? So what you have instead, you have these things called enzymes. And again, an enzyme is a catalyst. So again, it's not used up, but what it does then basically is it lowers that activation energy, and it makes it easier for the reactants to be turned into your products, whatever that is. So most of the time, this happens something like this. So for example, here is sucrose. So you eat some table sugar in your body. What happens? Well, that sucrose has to be broken apart into two things, glucose and fructose. Well, normally in your body, that would take forever for your body to break down sucrose because it's just a very high energy process. Your body has this enzyme called sucrase. And sucrase drops that activation energy and makes it really, really easy for your body then to break down sucrose. So normally the way that happens is you have this kind of a thing. It's fun. Like this. Where you have an enzyme, and on that enzyme, you have a little certain pocket called an active site. Now, an active site is shaped exactly like the molecule that it's trying to make react. So, for example, sucrase has a little hole in it that's shaped just like sucrose. So sucrose flies around, and it fits right in that pocket. And when it gets into sucrase, the sucrase helps it then to break apart that sucrose into glucose and fructose. So sometimes called a lock and key mechanism. In classical biology, called a lock and key. So you have a little certain keyhole shaped exactly like the sucrose. And the lock is the sucrose. It comes in, turns it, does it. I mean, super quick, super easy that way. And your body has dozens, hundreds of these enzymes in your body. So for example, another one. Lactase is probably one you've all heard of, or maybe not. But lactase is an enzyme that helps you to break down milk sugar. It's what I call lactose. So someone, for example, is lactose intolerant. It means they don't have lactase. So their body then has a much harder time than trying to break down lactose. Okay, so like I said, to most people then, it's super easy. Right? They have, let's say, here's the lactose turned into the products, right? And they have an enzyme that makes it really easy. But a person knows a person though that's intolerant doesn't have that, so it's much harder for them, to turn that lactose into its products. Okay, so that's one. Another very common one are called peroxidases. So oftentimes in your body, oftentimes in your body, you're either making peroxides or you're ingesting peroxides, and most peroxides happen to be poisonous. But it's no problem, though, for your body because you have this enzyme called peroxidase. And it's just always constantly scouring your body trying to find peroxide. Once it does, it immediately pulls it into a little pocket, breaks it apart, spits it back out, and then you're fine. Okay? Another one is this one, acetaldehyde dehydrogenase. This is a long one. Yeah, acetaldehyde dehydrogenase. And this is common then for what's called the Asian flush syndrome sometimes, or alcohol flush syndrome. A lot of Asians have this, but they don't have this enzyme, so they have a beer or two, and their face gets glowing hot red. My wife's Korean, she does it. She has like one beer, her face gets like bright red, really, really hot. Right? I've seen this before with Asian friends or something, or family. Yeah, so that's another one. So what happens then? Well, then normally then what happens in your body, then you have a beer or a wine, and your body begins to break down the alcohol, and one of the steps that it gets to is breaks down the alcohol into this stuff right here, acetaldehyde. And most people's bodies, like I said, it just goes on fine, breaks down that to the next step. But if you're missing that enzyme, though, then we can't break it down as easy. So the acetaldehyde in your body then builds up and builds up. It just takes a lot longer to break down. Gives you all these symptoms, and like I said, with really red, flushed skin, you get really hot and sweaty, and all this kind of stuff. So that's another one. Yes?
Is it deadly? Life-threatening?
No, it's not deadly. No, not at all. Nope. And then another very famous one is this one, acetylcholinesterase. And acetylcholinesterase is a very common one in your body. And what it does then is it breaks down this stuff called acetylcholine, which is a neurotransmitter. If you've had a class in biology, you might have heard this before. So in your body then, normally what happens is you have a nerve, let's say, and it fires off and tries to send a signal to your muscle or your brain or whatever to do something. So what happens then is you have your little synapse here, right? So here's your nerve, and here's your receptor over here, let's say, okay? So your nerve fires off, and it sends off a little transmitter. And the little transmitter molecules are this stuff, acetylcholine. So normally what happens is the nerve fires, sends off the message is received, acetylcholinesterase comes in, then breaks down the molecule, breaks down the molecule once the message has been received, right? But if you can block this stuff, then it's a very nasty thing, because what happens then is your muscle or nerve, whatever, sends that message, and it keeps sending it over and over and over. So this is the root then of many then of like the chemical warfare nerve agents. So what they do then is they actually target this enzyme, and they actually bind up this enzyme so it can no longer take in the neurotransmitters. So your muscle sends a signal to your arm, to do something, or your leg to twitch or whatever, and it keeps sending it over and over and over and over and over, because it's never stops sending it. Does that make sense? So it goes over here. Like I said, it goes over here. Okay, arm twitch, and then it breaks it down. But if it doesn't break it down, it keeps telling your arm to twitch, 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 twitch. So this is, like I said, this is used like in all kinds of chemical warfare agents of really nasty, nasty stuff. But normally, though, this stuff is crazy efficient. I mean, you cannot believe how efficient it is. It has what's called a turnover number of 7.4 times 10 to the 5th molecules a minute. So that's 740,000. So that means every minute, just one enzyme can actually reach out then and grab an acetylcholine, pull it in, break it down, and spit out the products. And it can do that 740,000 times a minute. 740,000 times a minute. So what would that be a second? Divided by 60. So roughly 12,000 times a second. Imagine that. Take it in, break it, spit it out. Take it in, break it, spit it out. Take it in, break it, spit it out. 12,000 times a second. A second. 1001. 12,000 times it just did that. Crazy efficient. Well, so enzymes, like I said, they only do one thing, but they do it really well. They're just finely tuned. Like I said, they're going to break down lactose, or break down sucrose, or break down peroxides. Okay, so like I said, so all these things are just examples of catalysts. So again, a catalyst is something, like I said, they'll help you speed up a reaction, but it's not consumed in the process. Okay. So let's just look at a few examples here and see, okay, so what do I think this would do to the rate of the reaction? Would it make the rate faster? Would it increase the rate? Would it make it slower? Or would it have no effect? So pull out your hand out if you have it, and let's take a few guesses here. So I would just let you go through all five and just have a guess. Talk with your neighbor there if you want, and see what you guys think. So just take your best guess and talk it over. So will it increase, get faster? Will it decrease, get slower? Or it won't matter. Nothing's going to happen. It will have no effect. So write down your 5 guesses and then compare with your neighbor. Okay. Well, you have 5 guesses written down. Find somebody behind you, next to you, in front of you. Look around. Say, hey, what do you think for A, B, C, D, E? And talk it over if you don't agree.
Does it increase, and I think this one is no change. Yeah.
Oh yeah, the increase. So yeah, and then this one's not change.
I think so.
Oh, that's true.
Okay, talk it over. Find somebody. Okay, do you agree with your neighbor yet on all 5? So you're either all wrong or all right together? You're all going down together? Okay, so the first one, if you heat it up, if you increase temperature, what's it going to do? It's going to make it faster. Yeah, it's going to increase the rate of reaction. Yes, again, right? So faster, so that means, more collisions, harder collisions. Yes, it's a good thing. What if you reach into the reaction and you actually pull out some of the reactants, so you don't add as much of the reactants? That's going to slow it down, right? It's going to decrease it. Why?
Because there's less reactants.
Okay, so less reactants means fewer collisions then too. Yes, so yeah, fewer collisions. How about the next one? You add a catalyst in there.
I put increase.
Yes, it increases the rate. Absolutely. Yes, it makes it much faster. Yes, it makes it much, much faster. That's the whole point of the catalyst, is to make it faster. Another example, by the way, for that is the thing in your car called the catalytic converter. I can't spell something. The catalytic converter is exactly this. It has a catalyst in it. So that's why it's called a catalytic converter. And what it does is it helps to break down all the poisonous, toxic gases in your exhaust into less nasty stuff. And again, how to do it? With the catalyst. It has a little catalyst in there. And same thing basically. So your little gas comes through there. The catalyst grabs the gas, breaks it down really quick, and spits out less nasty exhaust. And breaks it down, spits it out, and breaks it down, spits it out, and breaks it down, spits it out. But it's not being used up, which is the nice thing I said. So you can do that over and over and over for years and years and years without being used up. How about the next one? You put the reaction into some ice.
I put slows it down.
Yes, it decreases, slows it down, right? Because again, colder means slower, so less collisions, easier collisions. Going to have a slower reaction. And what if you increase the amount of the reactant? Increase or increase? Yes. Again, more of them, that means more collisions. Yes. Awesome. Okay. Okay, one more time. Try these. Take your 4 guesses and then compare your answers with the neighbor there. Talk it over if you haven't yet. Find somebody. Maybe they're in front of you, behind you, there's nobody by you.
Increase, decrease, increase, decrease. So good.
Okay, real quick. The first one. Increase, decrease, or no change?
Increase.
Increase. How about the next one?
Decrease.
Decrease. How about the next one?
Increase.
Increase. And the last one?
Decrease.
Decrease. Increase, decrease, increase, decrease. Okay, any questions on those? Awesome. Okay. Now, I've got to tell you something though. Now, up to this point, I've been writing reactions with a little single arrow for the most part. But most reactions are not really a one-way street. I mentioned this in lab briefly last week. But most reactions do not go all the way from reactants just to products and then they're done. Most reactions actually are what's called reversible. So the reactants combine and make products, but then the products recombine and go back to make reactants. So you actually have a forward reaction where the reactants are going to products, but then you have a reverse where the products are going back to reactants. So it really is then more of a two-way street. So that's why we use a little double arrow like this instead of a one-way arrow. And that's called an equilibrium arrow. So that just shows, yes, reactants do go to products, but products also go back to reactants. So we use a little double harpoon there thingy looking. So reactants go to products, but products go to reactants. So we have both happening in most reactions. So yes, we're kind of lying to you. It's not really a one-way arrow, really. Most of the time it's not. There are some. Okay, so this is our little equilibrium arrow. This is our new friend right here. Right there. Two-way street, okay? Okay, so let me show you here what I'm talking about. If my thing will respond. Okay, so normally what happens then in the reaction, when you first dump in your reactants, it's super fast because you have the highest concentration of the reactants at that point. And then the reactants begin to react and make product, and react and make product, and react and make product. Well, as the concentration of the reactants is being used up, well, you're going to have fewer and fewer of them, so it makes it harder and harder then for them to find one another, so it gets slower and slower. So, if this was the rate of the forward reaction, well, at first, it's 100% reactants, no products, so it's really easy for them to find a buddy. But then over time, they're used up, and now it's a little harder to find a buddy, and it's a little harder to find a buddy, and it's a little harder to find a buddy, so it gets slower and slower and slower. Okay? But in the reverse, though, is just the opposite. So the reverse way, the products go into reactants. Well, at first, there are no products, right? So there are no products present. But over time, as you begin to make them, well, now it becomes a little easier for them to find each other and to go back to reactants. A little easier to find each other, to find each other, to find each other. Until you reach this point where the rate of the reactants colliding and turning into products is the exact same as the rate of the products colliding and going back to reactants. And at that point, that's what's called equilibrium. But it's normally called a dynamic equilibrium because it is still constantly moving. It is constantly dynamic. It's not static where it's stopped and the reaction has stopped turning reactants into products and vice versa. No, it is still going this way and this way, but the rate is the same in both directions. So the rate of reactants going to products is the exact same as the rate of products going back to reactants. They are equal, which is why it's equilibrium. But it is still happening in a big circle of life here thing, so it's dynamic. Okay, you're giving me the blank look. Are you okay?
So it's basically the same speed of the reactants turning into products and products into reactants?
Yes. So let's say, for example, it was that one I showed you earlier. That was horrible. Try. Let's say it was 2 COs plus an O2, I think it was. Goes to 2 CO2s. So, at first, all I have is COs and O2s, right? So at first, all I can do is I have a whole bunch of COs over here, right? A whole bunch of COs, whole bunch of COs, whole bunch of COs, and have some O2s in here too. Have some O2s, have some O2s, have some O2s. Really messy, sorry. So at first, all I can do is go forward, right? All I can do is begin to combine COs and O2s, get rid of them, and turn them into CO2s, right? And then I combine another CO and an O2, and I make a CO2. Then I combine another one, and I make a CO2. Well, over time, it gets harder and harder for this reaction to keep going because they're being used up, right? The reactants are being used up. They're going away. Right? That makes sense? So it gets slower and slower because they can't find a buddy they need after a while. But the reverse is also true. At first, there was no CO2, so there was no reverse reaction. But over time, as you make some, it's like, oh, hey, there's one. Oh, hey, now there's two. And now these two can find a buddy and go back over here. So over time, this one gets slower, slower, slower. This one gets faster, 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 until it's the same in both directions. Does that make sense? That's when the equilibrium happens. When the rate of these turning into CO2 is the same as the rate of CO2 turning back into these. So it's still going. It's still circle of life in here. We're going around, going around, going around. It's not stopping, but just the rate, both directions is the exact same. So that's the equilibrium we're talking about. Okay. So let me give you a little example here. Let's say we have H2 and I2 goes to H2HIs. So at first you dump in H2 and I2. There is no HI, right? So all that can happen is H2 bounces around, tries to find an I2, they collide, they collide, they collide. At some point they actually collide with enough energy in the right orientation, and they recombine, and they make two HIs. So at first, it's all reactants, there's no products, right? And then over time, okay, oh, well they actually collided and they made a couple of products. So now it's a fewer reactants, a little more products, right? And then over time, oh, it's even fewer and fewer, until you reach some point where it's going to be equilibrium, where the rate of the reactants going to products, same as the rate of the products going to the reactants, and that's when you have the equilibrium. So at that point, it's steady. It's equal. Now equal does not mean equal concentrations. Equal means equal rates. The rate of reactants going to products to the rate of products going to reactants. It does not mean, oh, they're 4 to 4. That's not what it means. It doesn't mean equal concentration. It just means the rate of the reactants going to products is happening at the same speed as the products going back to the reactants. So once you reach that, then it says steady concentrations, steady concentrations. Not equal concentrations, but just steady, 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 steady. Okay. Okay. Well, let's look at a general reaction. So write down this reaction. Little a, capital A, plus little b, capital B, is an equilibrium with little c, capital C, plus little d, capital D. And this could be any reaction, right? So maybe that's, so these lowercase numbers are the coefficients, like 1 or 2 or 3, and A would be the molecule. So 1 CO2 plus 2 NO3s or whatever they are, right? So we're just writing a generic reaction. So what I can do is I can write a nice little expression that tells us, okay, once I reach equilibrium, what is the amount of the products compared to the amount of the reactants? Because it's not always equal, but well, so what is it? So I write a little thing, call it a capital K, and you either see it written capital KC, which is for concentrations, or KEQ, which is for equilibrium. You'll see it written both ways. So what I do is I take that and I write it as a little ratio. I'm going to put, the amount of the products over the amount of the reactants. So these little square brackets, that means concentration. And for us, that always means molarity, molar concentration. So the molar concentration of product C to the little c power. So whatever that coefficient was, 1, 2, or 3, to the 1, 2, or 3rd power, times the molar concentration of D to whatever its coefficient was. Divided by the same thing for the reactants. Okay. So again, those square brackets, that was horrible. That means molarity. That's the molar concentration. So the molar concentration of C to the little c power. Molar concentration of big D to the little d power, etc. Now again, they're not equal concentrations of products and reactants. If they're equal and equal, will just be 1. It'd be the same thing divided by the same thing. So it's not going to be. But again, what's equal is the rate they're going back and forth is the same. So let me show you an example. Let's write an equilibrium expression, a K, for this one. 2, remember how to name that? N2O5? Dinitrogen pentaoxide. Yes. Goes to 4 nitrogen dioxides and an oxygen. So, if I was going to write a K for this, I'm going to write KEQ. I'm going to put concentration of products on top over reactants on the bottom. So my first product was NO2. So concentration NO2. So again, make sure you use square brackets. Little curvy brackets or parentheses. To the 4th power, because of that little 4 coefficient. Times concentration of O2. And there's no power there. I mean just a 1, because it's just 1 O2. Over the reactants, concentration N2O5 to the 2nd power, because there was a 2. Right, so that one there, that one there. With me? Okay, so whatever this number is, this tells me, okay, so once the reaction has kind of settled down into a nice rhythm, is it mostly products? Is it mostly reactants? What's that ratio of reactants to products? And that again is called our equilibrium expression, our K. Okay. So your turn. Try a couple of these. So how would you write a K for that first one? N2 plus O2 goes to 2NO. Write that one down. You don't have your hand up. I'm going to hide this slide for a second. So hopefully you have that written down. Whoops, didn't do that yet.
Square bracket.
Majority right here. Square bracket. So K. Oops.
E equals
Yep, equals square bracket into
square bracket
times square bracket.
O2
Okay, oxygen. Okay.
divided by
Okay.
square bracket NO.
NO. Okay.
Square bracket and
Uh-huh.
2.
Oh, thank you. Not okay, right. 2. Great. So what you got? Nope. Why not? Products over reactants. Products over reactants. So, what is it?
My bad. The other way around.
So it's really products over
And
reactants. Yes, the other way. A little better. Products over reactants. Okay? Let's see if this is finished here. Yeah. Not quite. Okay, how about the next one? Let's see what the next one is. Try to get my little thing here to update. The next one was N2O4 goes to 2 NO2s. N2O4 goes to 2 NO2, so try that one. Okay, compare. Then try that next one when you get done too. Okay, so for the next one, you should get what's going to be on top? Concentration of what?
NO2.
NO2 squared, right? Over concentration N2O4. How would you name that, by the way?
Dinitrogen.
Dinitrogen. What's 4?
Tetraoxide.
Tetraoxide. Right. Okay, good. Okay, how about C? How would you do C? Concentration of what on top? SiCl4 times
H2
concentration of H2 squared, right? Over concentration SiH4
CO2
times concentration of CO2 squared, right? Okay, so there you go. So that tells you, okay, once the reaction has reached equilibrium, what's the ratio of my products compared to my reactants? Awesome. Okay, good. Work with me here. Now, one interesting thing, though, to think about is in that equilibrium constant expression, in that K, we do not include solids or liquids. Why is that? Because the concentration of a solid or a liquid is always constant. In other words, I cannot take a solid or a liquid and make it more or less concentrated.
Can you repeat that? So on equilibrium we do not use.
Do not include solids and liquids are not included. So for example, let's say I have a chunk of salt, solid salt. I cannot change the concentration of that salt and make it saltier. I cannot cram more salt into the same volume, into that same salt block. It is already as concentrated as it can be. Same thing with water, a pure liquid. I can't make water extra waterier. I can't make it less watery. It has a constant concentration. I can't change it. But if I have salt in water in a solution, that I can definitely add more salt into the water, or I can take out salt. I can change the concentration of the salt, the aqueous. But I can't take pure salt and somehow cram more salt into that same space. Or I can't take pure water and cram more water into the same volume, make it waterier. Are you with me? So pure solids and pure liquids we just don't include in the K. So for example, right here, calcium carbonate solid goes to calcium oxide solid plus CO2 gas. The K expression, I don't include the solids. So it's just CO2, oxygen CO2, that's it. Yes?
Just for that, in a hypothetical situation, if calcium carbonate was a gas and CO2 was a solid, would Kc be written as 1 over CaCO3?
Yes, very good question. He's going to show you those here in a little bit. That's a very good question. Yeah, so excellent question. So what if these were something that was a gas? I'll just put 1 over that then. Yeah, because nothing over here, so just put a 1. And I'll show you one of those here in a second. But basically, so that means, what do you include? Aqueous and gases. Don't include solids or liquids, so what's left? Aqueous and gas. Because a gas you can make more concentrated, right? You can take a gas, you can always add in more gas into that volume, or you can suck out gas out of that same volume. Okay, I'm not sure if you are convinced or not. So let me draw a little picture here. Another one of my lovely patented drawings. So let's say I have a block of salt, and it has all of these sodium chloride ions packed in here. So that has a certain concentration, a certain amount per volume, right? Moles per volume concentration. I cannot make that more concentrated. They're already packed in as close as they can possibly get, right, in a solid. So I can't cram in more salt into that same volume, make it more concentrated. And I can't reach in there and just pluck out random ones to make it less concentrated, right? There's no way to change the concentration of it. Does that make sense? The only way then to get more salt is to get more volume of it at the same time, right? So to get more salt, well, I need more volume of it too, right? Because concentration is moles per liter, right, per volume, right? Amount per volume concentration. How about water? Well, if I have a glass of water, let's say it's my water, again, it's got a bunch of waters and they're all packed in here, as tight as I can get them, basically. So I can't take that volume of water and make it more concentrated, right? I can't cram in more water. There's no room for more water. That makes sense? So I can't make it even waterier water, right? It's already as watery as it's going to get. And I can't make it less watery by reaching in and pulling out molecules. Because if I do that, well, then I also change the volume at the same time. So it has a set ratio of amount per volume for solids and liquids. But a gas, I totally could. Let's say I had a gas in a container, and I only had a few molecules in here. Right? So here's a gas. Oh, well, a gas, I could totally change the concentration and pump in more molecules without changing the volume. Right? So I can make that more concentrated without changing the volume. Or the opposite. I could go in there and I could remove, right, make it less concentrated without changing the volume. So that I can adjust the amount per volume. Yes?
Won't I have a set constant when you reach the maximum volume, like gas you could put in a container, or no?
I suppose at some point there would be a maximum. Yes, you could. Yeah, right. There'd be a maximum. Mm-hmm. But you still include that amount because, I mean, it is variable. So you still include that amount because it could be anywhere from 0 up to whatever the max is. But a solid, it's always, I don't know, 12 or whatever it is. You know what I'm saying? It's always the same, so it's a constant, so you don't have to factor it in there. Water, by the way, I think is like 18.2 molar. So pure water is like 18.2 molar, I think, or something like that. And let's say you have a solution. Let's say you have salt dissolved in water. Oh, well, let's say here's, I'll use blue for water. How about that? Okay, well, yes. Well, that I can totally make it more or less salty water, right? I could add in a little more salt, and I could increase the concentration of the salt in the water. Or I could vice versa, right? So I don't know, with anything, right? Coffee, right? You make it more concentrated in the same volume or less concentrated. So, in other words, don't include solids and liquids, only include aqueous and gases. Okay. Oh, here's another one I just want to show you. For example, lead 2 chloride dissolves, is soluble, just a little tiny bit, not very much, as we know, to lead 2 ions and 2 chlorides. How would I write that? Oh, well, I wouldn't include the solid. So it'd just be concentration of lead, concentration of chloride, squared. So only include gases and aqueous. Gases and aqueous. Okay, pull out your handout. Let's look at the first one on that handout. Carbon plus carbon dioxide makes carbon monoxide. So practice writing that and compare with your neighbor when you get something. See what they think. Okay, compare that first one, if you haven't yet. C plus CO2 goes to CO, or 2 COs. What do you think? What for the K? Do you and your neighbor agree? What'd you get for that first one? Okay, so the first one, what'd you get? Concentration of what? CO squared over concentration CO2. Is that what you got? No? Yes?
Yeah.
Awesome. Okay, try the next one. Try the next 4 there real quick if you haven't.
Professor, what if you have concentration of CO2? No, CO squared over CO. Would you be able to cancel out, just be CO?
I guess so, huh?
Technically speaking.
Yeah, you could. Yeah, huh? Yeah, I guess you could. Can't think of where that would ever happen, but
I'm just like, I'm thinking like.
no, yeah, but you could. You mathematically, sure. Yeah, you have x squared over x. You can
Yeah.
cancel out 1. Yeah,
I was just thinking that.
yeah. Okay, how about the next one? What'd you get? Concentration of what over what? CO2 over CO, right? Because you don't include this solid or that solid. Okay, looks like most of you are done. If you have the handout, you are. How about C? Concentration of what over what?
CO2
CO2
and
over
PCl5
PCl5. How would you name that? Phosphorus pentachloride. Yeah, you'll say mono though for the first one. The first one, the one you say phosphorus pentachloride. Okay, good. Okay, somebody else I haven't heard from. What would you do for D? What would D be? Who haven't I heard from? D, concentration of what over what?
Is the test going to be this easy?
This is that's pretty easy, yeah. This part is. Somebody haven't heard from anybody over here care to give me an answer? Okay, what'd you get, Marlies?
Potassium nitrate
Yeah, concentration of potassium nitrate
2
squared, right?
or squared, yeah.
Right, okay.
Over lead 2 nitrate.
Good job. Lead 2 nitrate, yes.
And KCl, potassium iodide.
Potassium iodide
Squared.
squared. Yeah, good. So KNO3 squared over lead 2 nitrate times potassium iodide squared. Right. Okay. And E is the one that Reed was asking about. Kind of like, well, what do you do if you have all solids on the reactant product side and that? So what is that one? What is E? 1 over what? O2 cubed. Right, concentration of O2 cubed. Yes.
In a hypothetical situation, if it's all solids or all liquids, is it 1 or is it no equilibrium occurs?
It's 1, yeah.
Okay.
Yeah. Yes.
So like same thing on the other side, if you had all solids and liquids on your products, it would just be, or the other way around.
Okay, well, let's just try to calculate some numbers now for this. So now let's just write our K. And let's say, okay, so this reaction was allowed to run, and we measured the concentrations once it stopped changing. And we got the H2 was 0.11 molar, the I2 was 0.11 molar, the HI was 0.78 molar. What's the value for that K? What is that K? So I'm going to do it here with you. So let's take it and write the K. The K will look like concentration of HI squared, right? Over concentration of H2 times concentration of I2. So far, so good? Is that what you would have written?
Yes.
Hopefully. Okay. So now let's just plug in our values. So what's the concentration of HI? 0.78. And we're going to square that over, what's the H2? 0.11 times what's the I2? 0.11. So we'll punch that in our calculators.
Yes. So when you're doing that, you don't use is it? You use parentheses instead of using brackets.
I mean, you can use the square brackets if you want, but square brackets only mean put in a molarity there.
Yeah.
Well, that means, yeah. So once I put in my molarity, I don't have to necessarily keep it for that. So what'd you get? I got 50. 5.0 times 10 to the first. You want to do, or just 50 points, right? That's what you got? Okay, notice K has no units, by the way. There's no units on equilibrium expressions. Note to self, there are no units on equilibrium expressions. K is just a number. There are no units on equilibrium expressions, so don't try to put, oh, molarity square, or molarity to the negative, whatever. Nope. It's unitless. All it is purely a ratio of products to reactants. So in this case, a ratio of 50. Oh, well, if it's products over reactants and it's a big number like 50, that means I must have more products than reactants. Because I'm dividing by a bigger number. I'm not dividing by, the number on top must be bigger than the one I'm dividing by, so I got a big number. Yeah.
Does this calculate Kc? Does Kc equal Keq?
Yes, it's the same thing I mentioned. Yes, yeah, same thing. If you either here call it KEQ for equilibrium or KC for concentration, but it's the exact same thing. Yeah. Okay. Let's try another one. Let's say they gave me the concentration of this and of this, and they gave me the K, but they want me to find this concentration. So so we can just write our little expression here again. So I write my K, what do you want to call it, C or EQ, doesn't matter. It's concentration of CO2 times concentration of carbon tetrafluoride over concentration of COF2 squared, right? So we're going to plug in what we know and rearrange and solve for what we don't. So we want to find CO2 right here, right? So you can either go ahead, rearrange it now and then plug in, or plug in and then rearrange it. I don't care. I normally rearrange it first, like I did before with the gas ones. So the concentration of CO2 would be Kc times the concentration of COF2 squared over concentration of CF4, right? Or you could just plug it in here. It does not matter how you do it. You could have plugged it in here and said, oh, 2.00 equals concentration CO2 times CF4 was 0.118 and COF2 was 0.255, and solve that way. Either way, however you're more comfortable. Do this way is going to be KF is, oh, I'm sorry, squared. That one was squared, right? However you want to do it. Either rearrange it first or just plug it in and rearrange it later. Your choice, whatever makes you more comfortable with your algebra. Just plug it in and then solve for the missing value there. So carbon dioxide. Let's hear some numbers.
1.1.
1.1. Same? No.
1.10.
Let's see what I got. Yeah, 1.0. And that's a square bracket concentration, which means it's molarity.
Right.
Yeah, the K has no units, but concentrations are molarity. So capital M in italics, or capital M with a little line under it, or whatever you want to do. Right. Perfect. Okay. Okay, your turn. Try that one. Write the K and then calculate it, and there's all the concentrations that were measured. Once it reached equilibrium, we found these values. So what's the K? Yeah, so you just write your K expression. So K equals concentration of CO times concentration of H2 cubed over concentration of CH4 times concentration of H2O equals, see, the CO was 0.81, right? The H2 was 0.28 cubed, don't forget to cube it, over the CH4, 0.13, and the H2O, 0.53. What'd you say, 0.26?
Yeah.
Awesome. Okay, try another one. So now they give you the K and two of the concentrations. I want you to find the third concentration. So what's the concentration of sulfur trioxide? So we got so the Kc will look like concentration of sulfur trioxide squared, right, over concentration of sulfur dioxide squared times concentration of O2. So again, you go ahead and plug in everything you know now and then solve, or you can rearrange it and solve. What are you going to do? I guess I'll plug it all in here. Let's just plug it all in here and see. So 680 equals concentration of sulfur trioxide squared over, what's SO2? 0.300 squared times O2, 0.150. Okay? And so you wind up getting SO3 squared equals what? Somebody tell me? For the square part, did anybody get that? Or you do it
It's
all?
like 9 something.
Nobody got that? SO3 squared equals something?
It is
So-
9.18.
9 okay, so 9.18. So what's the concentration of SO3 then? Well, if I'm going to get rid of a square, what do I got to do? Square root it, right? So I'm going to do the square root of 9.18, right? I got to square root both sides. Are you with me? To get rid of the square? Yes?
Yes.
So what is it?
3.03 molar.
3.03 molar. Stupid thing.
Can you explain after the second step? So the SO3 squared equals 918. How did you get the 918?
Okay. So, whoops, wrong one. 680 is going to equal SO3 squared over whatever that thing is. What is that? Did you do that part? Did you do 0.3 squared times 0.15? Sorry, I'm sitting down, but I'm fighting a horrible cold and I have like no energy. Sorry. 0.0135. So, what do I do now? How do I get rid of that 0.0135 on the bottom?
You divide this.
No. I want to isolate this, so how do I get rid of that thing on the bottom? I multiply both sides by 0.0135, right?
Okay.
And that becomes, whatever I said, 9.18 equals SO3 squared. And then square root of both sides would give me, what we said, 3.03.
Okay. Thank you.
Okay, a couple minutes left here. Believe it or not, we are almost through the chapter. It's a very short chapter. Not much to do in this chapter. But I kind of want to mention, though, what I was saying before about the magnitude of the K. Again, K is the ratio of the products over the reactants. So let's say K is bigger than 1, like really big, like 1.9 times 10 to the 19th. That's a big number. Well, that tells me the amount of products to the reactants. I must have what? Lots of products or lots of reactants if K is really big?
Lots of products.
Lots of products, right? Right? Because one number on top must be huge, and the one divided by on the bottom must be really small. So if K is large, that means the reaction is way favoring products. It is going largely in the forward direction. Right? It must have lots of products compared to reactants. So a K that's larger than 1 means more products than reactants. Okay, how about the opposite? Let's say K was small, like 4.1 times 10 to the negative 31. That's 0.0000, 30 times 41. Really tiny number. Oh, well, if K is really small, it must mean then that we are dividing by a big number. And the bottom thing is the reactants, right? So if K is small, less than 1, we must have more reactants compared to products. You can just reason that out mathematically, right? A big number means a bigger numerator. A small number means a larger denominator, right? So big number, more products. A small number, more reactants. That makes sense in your head? right? Like if I had this, products over reactants. If it's this tiny of a number, that means I'm dividing by a huge number down here, and have a little tiny number on top, right? A little number here and a huge number here gives me a little tiny number. So I must have a lot of this, a lot of the reactants, right? Okay, 1 minute here. So that's basically what we're going to say. So if K is much less than 1, a small number, mostly reactants, we're favoring the reverse reaction. If K is about 1, oh, well, it's kind of equally split between the two. We're not really favoring products or reactants. And if K is big, forward reactions favored, mostly products. Make sense? Okay, we have, yes, 13 slides left is all, so we went out. Not much, and then we'll jump into 10, which is good. Which is good. We're supposed to actually, I think, finish 9 today, so we're almost dipped. So. All right, well, oh, crap, I have exams to pass back. I guess you can hang around if you want to. If you have to go to class, go ahead, and I'll give them to you on Wednesday in lab. If you want to hang around, I'll give them to you real quick. Marilia, Odalise, Chrissy's not here today, Araceli, Angel's not here today, Sasha, there's Candron too, Sydney, Aaron, Kendall, Angel. I have an answer key as well Wednesdays, so you can come and look at it. We'll go combine and see me, of course, in my office. Happy to go over with you, explain anything. Hilda. Three. Okay, and like I said, if it's your Scantron, I'll get to you Wednesday. Angel. He left. Lily. Marlies. Hilda. Reed. Marilia. Elise. Araceli. Sasha. Cindy. Aaron. Again, like I said, I have an answer key for you in class Wednesday in lab. You can look it over, or you can look by see me during office hours. Happy to look over with you, discuss anything, explain anything.
So it was Charles Gale's time? That was him?
Huh?
I don't know your credit question. It was
Jacques Charles. He was
okay.
French too.
Okay, so it's...
He was also French. Not the same guy, but he was French also.
I thought you were messing with the same guy with...
No, the same guy. No, different guy.